Logic as a discipline is concerned with the representation of reasoning and trying to find the basic principles of reasoning. Reasoning is obviously a form of thought. Now, not all thought is reasoning. When you're just thinking and lost in a daydream, or you have a loose, free association of thoughts, that's not reasoning. What must be in place in order for thinking to be reasoning? Well, presumably there has to be a certain structure to the thoughts. One thought has to pass over into another thought in a kind of disciplined way. And that passing from one thought to another is what we're interested in when we try to model reasoning in logic. Mathematical and symbolic logic offer extremely sophisticated tools for modeling and then thinking about large-scale properties of reasoning. But we have to make a few distinctions first so that we can clearly grasp the domain of investigation that we're involved in basic symbolic logic. So we're going to think of the units of reasoning as sentences, at least at first. So we have sentences or propositions, and what we want to do is be able to put together many different propositions in such a way that they form an argument. An argument is a set of sentences where the sentences play different roles. Some sentences are premises in the argument, that is, the information you already have, and the conclusion is another sentence that draws implications from the information that you already have using logical principles. So if an argument is a way of drawing out new information from information that you already have, we want to think about different ways of doing that. So there's broadly three different types of arguments. There are deductive arguments, there are inductive arguments, and there are abductive arguments. Symbolic logic focuses on deductive arguments, and we'll see what that is momentarily. But in order to disambiguate this, let's look at the other two forms of argument first. That's what we're not going to be studying here. Inductive arguments are the bread and butter of scientific inquiry, in particular the empirical sciences. Why is that? Well, the fundamental nature of an inductive argument is to go from observed cases to make conclusions about unobserved cases. Here's a really simple and trivial example of an inductive argument. Suppose you've tasted 100 lemons in your time. You think to yourself, every time I've tasted a lemon, it's been sour. Now I've had 100 lemons, and I'm currently cutting up a lemon. So I conclude that the lemon I'm currently cutting up will be sour. What you've done here is you've gone from observed cases, where you've actually tasted the lemon and noticed a property, to an unobserved case, the lemon that you're going to taste in the future, and think that property is also going to be instantiated in the lemon I'm about to taste. So you've gone from past cases to draw a conclusion about what you should expect in a future case. You can see how that's the bread and butter of science because it deals with prediction. We're able to predict based on inductive generalizations what new observations we can expect to make. Other kinds of unobserved cases include cases that are not in the future but that are presently occurring somewhere where we have no observations. For example, on the other side of the Earth, or the other side of the galaxy, or the universe. If you think, every time I've experienced snow, it's been cold. Therefore, the snow in Antarctica is cold. Well, you're going from observed to the unobserved. You haven't observed the snow in Antarctica. You have observed other cases of snow, and you're using an inductive principle to draw conclusions about unobserved cases. You could then endeavor to travel to Antarctica and attempt to test your hypothesis by actually observing the snow there. And you can see that a large part of scientific activity consists in setting up inductive frameworks in which you can make these kinds of predictions or inductive generalizations. And the other part of scientific activity is figuring out how to test the hypothesis, which in some cases is not obvious how to do and involves figuring out how to measure certain parameters and so on and so forth. You can see how inductive arguments depend on things like having good data, having good empirical evidence, having large bodies of empirical evidence. Issues of sample size and so on are attended to inductive generalizations. Here's an example. If you ride in one taxi cab, and that's the only taxi cab ride you've ever observed, and the driver of the taxi was rude, and you draw the conclusion that all taxi drivers are rude, what you're doing is going from an observed case to unobserved cases, but you're doing so poorly because you only have one sample, and one sample is not sufficient to draw inductive conclusion. Other issues with inductive arguments are, how do we know that the future is going to resemble the past? Or how do we know that far reaches of the galaxy are going to resemble the parts of the galaxy that we can see in front of us? These are deep issues in the philosophy of science. You should also notice that inductive reasoning only draws probabilistic conclusions. If we were to observe a new case that acted as a counterexample to the properties we've observed in other cases, we would then have to revise our conclusion. So going back to the lemon case, the real conclusion that you're drawing there is that it's highly probable that the next lemon will be sour. But that conclusion is open to revision should you get a whole bunch of new samples in which the lemons are no longer sour. Now the probability of the conclusion has gone down. Abductive reasoning is the bread and butter of everyday life. This is the kind of reasoning that people engage in most often when they're not thinking about science or mathematics or anything like that. Abductive reasoning, though, is not limited to everyday life. It's also employed in science and philosophy. Abductive reasoning is what you do when you draw the best conclusion you can from incomplete information. Suppose you arrive home from school or work one day and you see your spouse's car in the driveway. You draw the conclusion that my spouse must be home. Now, you don't have all the information. You haven't actually observed the spouse in your house yet, but you come to the simplest explanation that best explains the information you do have. Now, strictly speaking, it's consistent with all the data that you have that someone stole your spouse's car and came and broke in the house. So really, there's a robber home instead of your spouse. That's consistent with the data that you've got, but it's not the simplest explanation for the data you've got. So this is most obviously where Occam's razor applies. That is, when you are in possession of incomplete information, draw the simplest conclusion that explains all the information you do have. Of course, this is also probabilistic. New information may run counter to that original conclusion. For example, if you get closer to the house and see a broken window, now you've got new information that you've got to deal with. And it may no longer be that the simplest explanation is that your spouse is home. You can see how that is what we do in everyday life. We're never in possession of all of the information that we need, and we're always trying to just find the best explanation for the information that we do have. That's partially what's so fishy about things like conspiracy theories. Some conclusions that conspiracy theorists draw are consistent with the data, but they're not the simplest explanation of the data, and they require extrapolating quite a bit out from it that doesn't seem justified. So they're failing in applying abductive reasoning in many cases. Deductive logic is no longer concerned with drawing probabilistic conclusions from data, but rather coming to understand what's conceptually entailed by the information that you have. As a result, the conclusions of deductive arguments follow necessarily from their premises. A deductive argument is one such that it attempts to preserve the truth of the premises. A good deductive argument, it has the following feature. If the premises are true, the conclusion must be true. Now, you can have deductive arguments in which the premises are false, but the point is, if they were true, deductive arguments draw necessarily true conclusions from the data. Presently on your screen is an example of a deductive argument. It's a very simple one. The more complex ones will come along soon enough. We have two premises leading to a conclusion. Now, there could be many more premises. This is one of the advantages of today's new logic over Aristotle's original deductive logic. It can handle any number of arbitrary premises. But here we have two. All mammals are vertebrates. Some sea creatures are mammals, for example, whales. Therefore, some sea creatures are vertebrates. What you want to see in this argument is that if these premises are true, the conclusion is guaranteed to be true. There's no way that the premises could be true and lead you to a false conclusion. That's how deductive arguments work. They preserve truth in the premises. They lay out ways of transforming sentences such that if you start with true sentences, you'll end up with necessarily true sentences. Here's a second example. Either the Lakers will win or the Rockets will win, but the Lakers didn't win. Therefore, the Rockets won. If these sentences are true, the conclusion must follow. That's the hallmark of a deductive argument. Here's a little bit more of a complex example, and it's not that you need to know all about number theory for the purposes of our course, but I want to show you why this kind of logic is so important, because it can handle mathematical reasoning very nicely in a way that simply no logical system prior to modern mathematical logic could do. Not Aristotle's logic and not Stoic logic. Very important. Our first premise is that for all numbers, either that number is prime or that number is the unique product of primes. Another way to say that is that all natural numbers are either prime or they are decomposable into a unique sequence of prime. 8 is not a prime number. Therefore, 8 is the unique product of prime numbers. So deductive logic tells you how you can take sentences and transform them into new sentences while preserving any truth that was in the original sentences. Deductive arguments, therefore, are highly idealized. They're not very frequently, in fact, used psychologically in our everyday life. This is one reason why students are often confused when they're in a symbolic logic class, because it's fairly divorced from the reasoning that occurs in everyday life. They're most at home when trying to represent reasoning that takes place in mathematics. But mathematical reasoning is the most ideal form of reasoning. So it gives us a model of reasoning at its most ideal, what reasoning would be in the best case. In that sense, it reveals something about the essence of rationality itself. Deductive logic is what we'll be studying in a course on symbolic logic.